Alrighty, last two problems on this set, problems 5 and problem 6. Problem 5 is this railroad problem. We got one train going from Bull Snake to Diamondback, or Copperhead, sorry, they're both stopping at Copperhead. Mean of 170 minutes, standard deviation of 20. The other one's going the other way from Copperhead to Bull Snake. I think I got those, which is 200 minutes with a standard deviation of 10. It's actually Bull Snake, Copperhead to Bull Snake, Diamondback. This one should have been second one. Let's see. Yeah, doesn't really matter. One's going one way, one's going the other way. Anyway, the first question, and then these guys gotta wait if they get to that intersection before these guys, which seems a little silly, right? Because these guys are going a lot faster. So anyway, the first one says, what's the distribution of y minus x? So you got these two independent. It's going to be roughly normal. It's going to have a mean of y minus x, 200 minus 170, or 30. It's going to have a standard deviation of the sum of the variances, right? So 20 squared, 10 squared, square root. Part B in that problem says, over the long run, what proportion of days will the train have to wait? So we got this distribution. Waiting means these guys get there first. It means y minus x is greater than 0, right? So anything greater than 0, they're going to have to wait. Clearly a whole bunch of times, which we said at the beginning, right? So it's just normal CDF from 0 to infinity with a mean of 30 and a standard deviation of 500 about 91% of the time. And then we say we don't want them to wait. So let's hold on the departure, right? So if we hold the departure, how long do we have to hold the departure to make them wait? 1% of the time. So if it's 1% of the time, we're just looking for that z-score and converting that to a raw score, basically. So that z-score is 2.325. I did the z-score work here, which is the score minus the average divided by the standard deviation, not score but the time. You could also just do inverse norm of 2.325, right? Or sorry, inverse norm of 0.99 with a mean of 30 and a standard deviation of 500. Turns out to be 82.57, so about 83 minutes. And then this last one, problem number 6. It's got this swelling issue with the left foot, the right foot, and dominant, non-dominant. They give you all these numbers with swelling, and then whether or not they have that neuroma or that disease in the foot or both feet. Some have it left, some have it right. A couple have it in both feet, right? So the first question gives you a scatter plot of the ordered pairs with the left foot versus the right foot for the people, and it says there's two distinct group of patients. So we got these guys up here and these guys up here, right? So the guys up there in the upper left had a dominant right foot, and the guys up here in the right had a dominant left foot. You should go back and look at this. So you got to kind of compare the picture with the data too. And then they give us a scatter plot, second scatter plot, of swelling in the dominant foot versus swelling in the non-dominant foot. And what conclusion can you draw from this that you can't tell from there? And notice the strong positive linear relationship shoved over here to the right. So the basic thing that I can see is as the swelling increases in the dominant foot, it also increases in the non-dominant foot. Strong positive correlation there. And then it said, can we conclude that there's a difference between the swelling in the dominant foot and the swelling in the non-dominant foot? Give a statistical justification. So this, I kind of shortcutted this a little bit, sorry. It's a paired comparison. That's the important part of this one, right? Is it's the same people that we're comparing. So it's a paired comparison. So what you got to do is you got to take the differences between the 2 feet. Okay, so you could just put these in list 1, these in list 2, and just subtract them. But you're just doing a one sample t-test, right? It's not a comparison per se, it's a paired comparison because they're not independent. So put all the differences in list 1, then run the t-test. The null hypothesis would be the mean is 0. The alternatives, we want to see if there's a difference, so not 0. I got a test statistic of 10.68, p-value of basically 0, which means I'm going to reject the null, which means there is evidence that there's a difference between the dominant foot and the non-dominant foot. And the last problem says, use the measurements to suggest a criteria for diagnosing the neuroma and justify your suggestion graphically. So I didn't write down what I did here, sorry. The triangle ones, let me check my orders to make sure. The triangle ones are the ones, let's see, yeah, the triangle ones are the non-neuroma ones, and the circled ones are the neuroma ones, right? So We got this little comparison, so they're looking for a cutoff basically. So I just did a cutoff. Hey, look, all those over there. That cutoff right there, I didn't graph the thing. You can see it on here. It's about a 1.4. So anything more than 1.4, I think, based on my picture, would be evidence of that neuroma. So that's it for 5 and 6. Hope that helped a little bit.